Talk today, this one is Reactive Stream Processing using DDS and Rx. This talk is not about dentists and not about prescriptions, although I'm going to use both acronyms here. DDS is really, if you ask a normal person, it's a dentist, and Rx is, its really original meaning is recipe. It's a Latin word and it's kind of spelled that way. And modern meaning really means prescription. So I thought kind of interesting, But what I really want to talk about, most of it after this, is reactive systems, stream processing, those kind of things. How many of you have used, or do any sort of stream processing? Real time. Okay, one. And how many of you have used or have heard about reactive extensions? Okay, two. 3, and anyone who knows DDS, Data Distribution Service? Okay, so you'll find out what that is today. So that's my outline today. Stream processing, an overview of this. Some of you know already over DDS, and we're going to combine these two in a demo and see how they really fit well together. So reactive systems, right? These are sort of systems that everybody wants to build. I mean, who doesn't want elastic, event-driven, resilient, and responsive systems? Everybody wants to have those characteristics. And of course, people have been building these kind of systems that have these capabilities for decades actually. But what's new this time? Well, there is a new style of doing it, reactive style, and it's based on event-driven, modular, pipeline, asynchronous operations, and in some cases it's more like functional. Many times this reactive extensions particularly, it doesn't have to be functional every time, but that style is very dominant in this domain. So it's almost like hard to separate those things out. But there is really no fundamental reason why you couldn't build a system that is all of this without using a single functional programming concept. But somehow functional programming makes it really easy to do it that way in code. So using a higher level of abstraction, I need to say. We'll look at that in form examples. Stream processing. So how is that related to stream processing? Essentially, if you think of an application that has a shape, and shape kind of looks like this. Something comes in, things happen to that data, things get merged, things get split, over here, merged, splitting, all that, and something gets out. That's essentially stream processing. So it's an architectural style. You can imagine lots and lots of systems that are designed this way, and they are data just streaming through them, that operate on continuous sequence of data. There is really no end to the data, so it just keeps coming, and that's it. So again, the shape of an application concept, right? I think this is really important. So when you have a stream processing application, if you use, I feel, things like reactive extensions and DDS together, you can program, your code actually starts to look like how the application, how you conceptually visualize your application. Well, I know it's the first stage here, then this happens, and that happens, and then if that happens, then the data goes out, otherwise it's dropped, and something like that. So that notion of, there is a shape to an application. What if you could actually see that shape right in your code, and that you compile and it just does exactly the same thing as you want? And that's where functional programming comes in, and particularly Rx. So here is some completely arbitrary shape of an application. It's somehow doing lots of things, little things here and there. Let's not look at this for now, because these are sort of Rx operators that help you do with that. Chop out your application in little things. But that's the application. But then what if you have to do this independently over a whole bunch of, let's say, streams? If your application is really like that, right? It's essentially the same thing, pretty much. Over here, there is a merging of 4 things, there are only two things over here, but then once you are through that, it's essentially like going in parallel. So if you could write application just by saying, well, my application really looks like that, and do the right thing when you see more streams of the same similar kinds. In some sense, parallelization, but that's not the point. But or at least focus to it. So that's the idea of the shape of an application. If you see that, you want to capture that, you might want to use things like this. And it's actually nothing new. So I'm sure you're familiar with Unix command line piping, right? I do an ls and -1 is like, okay, list all the directories in one column, and grep for search, it produces something, it's going to filter a bunch of things, and then I'm doing another grep for research, and okay, I just get one because I haven't got exactly one directory that says research, and that's it. So here, you have specified, well, your mental model is exactly reflected over here. Well, it's a list of things, it's directories, and filter everything that has research in it, and filter everything that has research in it. You never said read a file, open it, and then read the first line, then so do a find in it, and then should I copy it or not? You're just saying what you mean. It's like do this, do that, do the next thing, line by line. This notion of line by line is implicit in this programming model. It's going to be very similar, for events. We'll look at that. For events, if you could write it like this, it's a great plus. So a similar example. So list of files is really okay, static, right? Okay, I know all the directories there are, or maybe I know it's a file with 100 lines. So I know there are only 100 things that I have to process. What if something like this, right? Cat hyphen. So that's essentially whatever is you type in. You don't know how much you're typing. I know how much you're going to type in, but still you can use the same style. I think if you think about it, that's really weird as well as profound. I'm able to express the same thing without ever knowing what's my data. Over there, I knew that it's essentially directories, and I know how many there were. Here, I don't know what my data is. It could be infinite, but still it's the same programming model. You just pipe it and right things happen. In fact, nothing happens if you don't provide any input whatsoever. It just sits there quietly and does nothing. So I think this notion is very powerful, particularly for stream processing. And how do you capture that in using some of these tools? Any questions on this so far? It's probably just basic, just background for you guys. Well, that brings us to the first tool that we're going to look at today, reactive extension. This is something Microsoft developed a few years ago in .NET, in C#, and it is essentially a library for composing asynchronous and event-based programs. And the stream that we have been talking about has a type in Rx. It's called an observer. Makes sense. Okay, you can observe something, and that thing is observable, and I can observe it. So how do you do that? How do you observe it? Well, you have an observer, so you can observe that guy. It's an observable. It says that you can monitor me, and I have an So streams are really first class because you get this type called observable to deal with the streams, and everything else, the composition and different operators that you can latch onto are available. So it really feels first class when you're dealing with streams. You can do these kind of operations, you can filter them, you can project, aggregate, compose various things. The key, however, is it makes the programming experience very interesting as well as rather at some level elegant because of functional programming stuff. And it's available in a whole bunch of platforms, by the way. .NET, Java, C++, even C Ruby, Python, pretty much any language that has lambdas, that is essentially the core concept in functional programming. As long as you have that, it is very easy to use Rx very effective. Languages like C, you don't have lambdas, but still it exists. I haven't played with it, I don't know how the experience of it feels like, but it is very, very nice when you have lambdas in the language. So the next tool we have is DDS, that's Data Distribution Service. It's a reactive middleware. It is essentially a PubSub, publish subscribe middleware. You have publishers over here that just produce data. Think of them as sensors, right? If you have a flight coming in, and flight just produces data that I'm at this altitude just changes. It's just producing data, it lets others know about its location. And then there are flight controllers, there's your app that's interested in data for various reasons. Clearly, your app is not as critical as the flight controller, who has a job to make sure it lands safely. So there are a whole bunch of events that are coming towards you, and the real-time applications, enterprise applications that are interested in it. You just hook them up using DDS. The specialty of DDS is that it is used in real-time systems. I mean, these are big weird systems that if you don't have those in your life, it's basically storage. Like transportation, assembly lines, robots making your cars, big locomotives. The cars themselves tend to have like hundreds of processors these days in a modern luxury car, and they have to communicate in a very real-time fashion. So just to give an idea of where it is used. These are not enterprise applications. This is not that. And it's real time, pretty fast. DDS is a standard. There are vendors that implement it, and it spans really wide net in terms of its real time guarantees. And people have used it for hard real time as well as non-real time or enterprise things as well. There are a whole bunch of standards. This is just a quick overview of what DDS is made of. It's fairly big specification. There are a whole bunch of satellite specifications. Defense is primarily they use DDS quite a bit. Defense being one of the biggest users of DDS. So this ensures that your DDS app is portable across vendors. If you have a really large system, like imagine a battleship that is built by so-called integrators, right? Lockheed Martin, Raytheon, GD. These guys come together and they have to build a ship, and different pieces in the ship are built by different people and different companies. How do you make sure that when those things are put together, it's going to work? And that's a very big challenge that DDS addresses. And you have to be very procedural about that. It's not just one company. You can just tell your buddy next to you, okay, why don't you just change your header file and it will compile? No, it doesn't work that way. There has to be a standard. There has to be a given guideline. Okay, only after that things will start to work together. And lifetime of these systems are like decades. A ship probably lives 30-40 years. It has to maintain that. Now, one last concept here is about data centricity. So think about how you go about scheduling meetings in your office. Let's say you have just an email client. So Monday morning you get an email like, okay, you have a meeting on Thursday at 11 o'clock in room number 10. Okay, you make a mental note of that. On Tuesday, you get another email. Well, the meeting has been moved to 1 o'clock. It's not at 11. All right, fine, same place. Now, third email shows up on Wednesday. Well, the meeting has been rolled back to the same time, but now it's in room 15. It's like, wait a second. Now I have to it's the same time as of what? Same time as of as of Tuesday, as of Monday. So you have to shuffle through your emails, and you have to make sure that you are at you have to look at all the emails that you receive, make sure where you have to be, and then you will go there. But instead, think of it this different way. If you have a calendar application, like Outlook, it keeps track of your meeting. So Monday you get the first notification and it creates, it shows you as busy. And then the next email shows up, it automatically moves it up, from 11 to 1, it pushes it down, right? And then, okay, and on Wednesday, things change and you are in a different room with the different time. You don't have to go back when Thursday arrives. You don't have to go back and look into your emails like, where am I supposed to be? All you do is just, well, I have this calendar, I will open this up, I need to be here at this time, and that's it. It's essentially, it's trying to capture what's most relevant, what's the recent state of this thing called meeting that you're interested in. You don't have to go through 100 emails or 100 messages that were sent to you over the period of time to really get to, to where you need to be. So that's essentially the difference. That's how DDS works. In pretty much everything that you do, for instance, a flight coming towards an airport, that's the programming, that's the mental model you have. This is some updates. It's telling me about the location of this flight. It's not just messages. It's not just sending out. It is doing that. That's how it's implemented. But the concept is, okay, you have an object and you keep a state of that. And state management becomes very easy. So this is basically that example out here. Does it make sense? Our data centricity is not the same as just sending messages one after another. It's about the middleware makes sure that by liking this calendar application that moves things around for you, the middleware will do that for you in this case, DDS. So I already talked about publish subscribe. So I'm going to skip that. And now we're going to talk about how do these two things come together. Well, we have DDS for data distribution, and Rx so far is only for processing, right? I mean, you have a process. It receives data through this, let's just say, data readers, right? They're reading data. It could be anything. Your sensors, it could be the flight data, and you have to produce some data as a result of it, result of processing. Rx will help you in the middle. It doesn't care how data came to you. It doesn't care how you want to publish your data outside. It will just do your processing within. And chances are you have to sort of correlate things. Multiple things are coming in. Multiple aircrafts in the air at the same time, and then whatnot. So all those things you have to correlate when you are processing. So the library that I'm going to talk about is called Rx4DDS. It's essentially a wrapper written in C# that allows you to do this processing using Rx operators, because Rx is particularly suitable for stream processing and asynchronous processing, but here it's more like stream processing. And DDS is good at sending data around, so it's a great match together. So some of these things I'm really not going into because it requires a little more DDS background, and in fact my next two slides assume a lot of DDS background, so I apologize for that. So I'm going to skip these slides. If you are interested in how, the point here is that there are concepts in data distribution, essentially a distributed data flow, going from this machine to that machine to that machine to next. And then there are notions of data flow within a process, this one node within a process. It so happens that these notions are so compatible when you put DDS and Rx side by side. It's like you almost, you don't know which one you're talking about. Well, when you look at, well, this is a process, so it must be Rx, because really DDS doesn't exist within a process, it's outside. But you get to keep the programming model the same all the way from the beginning of your data. Doesn't matter how many hops it has to jump through the network and nodes. and inside the process as well. So you can literally draw a line from the sensor that goes through a node, a process, then another node, a process, another node, a continuous line to the end of it. And it's like just one data flow. And you can think of it, the whole application as the shape of the application concept, right? You can think of it that way. And with these two tools together, you can actually code it that way. So it's like self-documenting application, if you will. So we are pretty close to the demo part. So let me jump into that. So what I have here is a, by the way, any questions on this so far before we jump into, flying ships? Next. So what I have here, well, let's see it. Why not? So how to duplicate? Okay, good. So here's a very simple application sort of, and it's really designed to motivate the need of DDS and what capabilities it has. So there are going to be ships, okay? There are going to be publishers and the subscribers. So let me start from the beginning. What you see right now are two publishers that are producing data. One is producing data about squares. That's it. You could think of a real world application like a flight. And there is another publisher or another data writer that's producing data about circles. And by the way, circle happens to be green circle. You could have a blue circle, you have a red circle. It's like you have Delta flights, you have, I don't know, United flights and those kind of things. It's a flight, just a different kind. So let me start all over. So I'm going to publish a square, a blue square, and let me just start. There you go. It's just doing some silly things. And similarly, a circle. So another blue circle. Well, now let me go to my notes. I believe I had this order written over here in which order I should really do these demonstrations. So I can also subscribe to this data, okay? And everything is running on this laptop. By the way, I'm going to run a process here, and these two processes are going to communicate just within the same host, but that just happens to be because it's a laptop. DDS is really meant to be go across networks, right? So, well, not that one. Yeah. So, I'm going to subscribe to some data here, and there is no publisher. So, what do you expect? So, it's a triangle. I want to subscribe to anyone who is producing triangles out there, and you don't see anything because of course there is nobody talking about publishers right now. I mean triangles right now. So let's start one. So I have a simple program written here that generates values of those triangles such a way that it builds interesting patterns. I hope it works. Not quite a pattern so far, right? We're kind of bouncing around, trying to do something. There's probably some pattern, but we don't quite see it yet. So let's do an interesting thing. So I'm gonna stop this. I'm no longer interested in those triangles. So I'm gonna create not publish. I'm gonna create a different subscription, and this time around I'm going to say I want a history of 300. So what I just changed is, well, don't just give me the latest value. In fact, when you I want to keep at least 300 samples of this triangle around. I'm going to use it for whatever reason. In a sense, for trajectory, maybe you can think of it as a flight and last 300 known locations of a flight for different things. Similarly, well, just keep 300 things around. Let's see what happens with that. is going to display entire history on the screen for each point when there is data. Of course, there is no data so far. Voila. So now you see there is clearly a pattern here. So what's happening is there is exactly one triangle. Actually, there is exactly one thing being talked about, a green triangle. But it's just moving in interesting ways. But at the same time, we want to essentially keep its last 300 node positions, and it's trying to display those together. So now you see the whole pattern, what's actually happening. This history part is all DDS, okay, and we'll see why it's interesting. In fact, the reason I have this simple demo is just to give you what's happening in this demo. Then we will actually try to combine both Rx and DDS together. Any questions on this so far? Like what's running where, I know what we are looking at? Okay, let's stop that. And if you want to see what's actually driving it, let's open the code and look for flower. So this is C# Visual Studio, of course. Flower. I'm going to dive right into code with that example. So you're essentially looking at a very simple Rx program. Okay. Execution starts over there, flower, and there are some constants A, B, and C. Those determine the shape of the flower, essentially, how big, how small it is, those kind of things. And well, okay, the intent here is not to give a tutorial on Rx. Okay, I'm gonna walk you through this example, but if you lose me somewhere, then let me know. I'm not entirely sure which Rx background is really essential here, but I'm gonna walk through each line anyways. So we create an observable first of all, and we say, well, for each interval, like for every millisecond, produce a sample, produce a data. There is no DDS again so far. For every 1 millisecond, it's essentially going to produce one integer. 1, 2, 3, 4, 5, 6, that's it. Whenever you produce that value, I'm going to do some computation. I want to transform that value, 1, 2, 3, 4, into a location for the triangle. Okay, and just that computation is quite mathematical, as you can see. There is some sines and cosines being used here to compute. This is essentially a formula. As long as the values are between 0 to 360, essentially angle in degrees, it's going to produce x and y that fits somewhere in that box. And with increasing values of x, this x is going to move it a little bit so that it just forms this interesting pattern. Okay, getting back to the example. So maths is really not the point here, but okay, just think of it. Okay, integers come in and other interesting, they are transformed to something interesting, x and y values, essentially, a transformation. And here's the interesting part. There is a triangle writer. This is a process that's producing data, and the subscriber that's where you saw that data being shown is is consuming it. This writer is publishing triangles. It essentially says, well, write this value that you just gave me, x and y, and some color and shape, color being green. Just write it out. And there is a listener there is a subscriber that picks it up and just draws it. So there is nothing interesting in what triangle writer and where it came from. Just assume there is think of it as a socket that you write it out, write out data to. But it's more than that. It expects exactly these values, x, y, color, and shape size. Any questions on this so far? Like this is, give you a feel of.
So it looks like opposite, right? You subscribe for an event, but you are actually publishing.
So there are two applications. This code is what I ran over here. This window is your publishing data. The code you see is this window. Okay, it's publishing. Given some values of integers, it turns into x1.
Okay.
And sends it out. There is a subscriber that picks it up.
Okay.
Two different processes. They are communicating using shared memory in this particular case. They could use TCP or UDP for that matter. Now let's look at a different example. I'm gonna delete all these and forward. So now we'll publish some data using this application and subscribe right here. It's just a sort of UI. It's going to publish some data, it goes outside it, something happens to it and comes back. And it picks it up again and shows it to us. So I'm going to publish a square and a blue square. And some convention here. I'm going to for publication I'm going to use square and circles, and for subscriptions for all transformations you're going to see triangles. So triangles means this is after processing. This is what happened to the original source of data. I'm going to subscribe to triangles, and you're not going to see anything at all because there is no transformation happening in the system right now. So I'm going to start that. So this is actually forward shortest. I'll get back to what that means. What you see here is essentially it's doing very simple transformation. It just takes the old data, the data about the squares, and turns it into square. That's it, at the same location. So you can think of it as it just flips a tag on it. Like, oh no, that's no longer a square. It's actually a circle. Just make it a circle. A triangle. So it just picks it up, keep the same color by the way, and well, it just shows it over there because now there is a process that takes squares and produces out triangles at the same location. Is it making sense? So let's publish another square, a yellow one. What do you expect to happen? Yellow triangle, exactly. Because you just said, well, I want my application to do this thing, and that is, whenever you see a square, turn it into a triangle. Well, now I see two squares. What is it going to do? Just turn it into the other. So you just said what you want to do for one app, for one case, let's say, and the right things will happen for all the streams. So essentially there are two streams, aren't there? There is a blue stream, blue square stream, and there is a yellow square stream. You said what needs to happen for one, it started doing it for all. At this point you probably may not see like what's the big deal. It's like just a change in colors, like what's the point? But it will get more interesting later on. So
how many subscribers do you have now?
There is only one subscriber.
Right.
It is only subscribed to triangles, all kinds of triangles. So let's jump into the source code. In the meanwhile, I want you to think about how you might write such a program in your favorite language, in your favorite, middleware, TCP IP or what have you, get a rough idea of, how long it might be. Oh, it's a forward shortest. Right, obviously. Forward shortest it is 3 lines. So what we're doing here is, this time around I'm going to create a DDS observable, because now I'm going to consume data that's coming from outside. So I create a data reader that's going to suck in this data about squares. So I say, well, and it has a type. So this is way higher than sockets or anything like that. You basically say, well, I expect data to be of this type, shape type extended, and that type has X and Y and color and size. Very simple struct with four elements in it. And you're saying, well, it is being, whatever data is being published on this square topic, it's like, I want that, as long as, of course, it is of this type. Let's ignore participle. It is essentially, managing the whole, it's the container for those entities. And when that data is available, any data is available of this kind, just send it out to triangle writer. That's it. Isn't it exactly what you wanted to do? It's like, take data from here, write it out. Done. Your code has the same shape as your application. Get data, write it out. And you precisely capture that over here. There is no, like, okay, read this, and I don't know, I can't even explain, but it is as simple as you can get it. I think you have to write at least, it so happens that triangle writer is also aware of this type. So, well, that's why it kind of much smoother. You don't have to do any transformation. If like triangle had a completely different type, foo is being converted into bar, then there will be some more work. We'll look at that. But this is where it starts to get more interesting. It's like I can express my code and what I want to do in very simple, the command line format that we looked at a while ago, those kind of things.
So can you show the triangle writer definition?
Sure. The triangle writer is a data writer of this kind. That's the type. And let's look at the type of that shape. It's angle, angle and fill kind, and there is more stuff in it. Shape type, it inherits from shape type. So this is just the data, this piece. That's data in extended, and the original kind has color, shape, size, etc. So what I did here, so a very simple transformation going from one topic to another, as long as they have the same types. Now we will introduce interesting things between these two. And guess what? It is going to reflect the shape of your application, just like that. Because we're going to read some squares, write them out as triangles, but we'll do interesting things. So the next one I have is swap. How am I doing on time? It's 5:45. Swap shortest, I have a swap program. Guess what it might be doing? It takes X and Y from a square and swaps them out. The triangle that you see will have X that is old Y and Y that is old X. How do you write that? So it's essentially a projection. In functional programming and even in SQL kind of, in SQL or data processing, it's a projection. You have some data that's coming in. Now project it out as something completely different. You could generalize this in many ways. You can have more types, more members, fewer members, those kind of things. But essentially, it's a projection. Something comes in and a slightly different variant made of same ingredients. Like, you know, you get two things here, they get swapped, and you get output. In SQL projection, you may have a table of 10 columns, and you project out only 5 of them. So you look at only your input, and you do some interesting things with it, a projection. So that's how that's done using select. In Rx, that's essentially select. Oh, by the way, I'm not sure if I explained what's this, this between curly braces. That's actually a, how many of you are C# programmers? Okay, so you probably know that that's a lambda, essentially. So it just takes a shape value and produces a new shape. While doing that, it just swaps the values. For the new one, x is y and y is x. Everything else stays the same. So I just introduce this stage in between, and I'm showing a few things here. I'll get to it. The source is again the same. Now what is this thing? It's like one really wordy function here. Subscribe and dispose on completed. Well, what's happening is, when the original stream finishes, I want to also indicate that this transformed stream has also finished. Squares come in, and not just all squares. If blue squares end, I want to say, well, that blue triangle ended, but yellows can keep going. So think of a flight. United Flights lands. That doesn't mean all flights landed. It's like that stream ended, that flight is over, and all that. So anything that you're doing, your screens get updated, your app gets a notification, all that, and it forgets about it because, well, the flight ended. Exactly like that. So that's what we're doing. We're saying, well, when this original stream ends, that's the semantics of this function. Well, in usual case, keep writing what you get. But when it ends, when it is disposed, the original one is disposed, write that out as well. So essentially, just dispose it out. So let me do that here. And I think it's only going to work for blue in this particular case. So I don't know where the other program went, but anyway, let me show you how it works for blue squares. So it's the same program, right? Well, am I running the same right one? It's not the swap. Yes, I should be running swap. Delete all. Stop this. So the swap takes square as input. I'm going to start publishing blue squares. Oops. And swap shortest. Okay, nothing happens because we have not subscribed to triangles yet. Let's do that. And voila. It's sort of flipped now. If you see carefully, it's actually flipped x and y. So it's a transformation on it. Now let's dispose of the blue square. I want to say like this string ended. The way I do that here is dispose data and delete the source. Boom. So what you saw here, several things happen. So first of all, the GUI announced that this data that you see here is the string has ended. There is a cross in between, if you see, between the triangles, and of course it's no longer moving. But it's not just not moving, it knows that the stream ended. It's not like, well, these are the last 5 values, and I don't know what happened, I don't have any updates. It knows that it actually ended. So that whole information was sent over the network that, okay, it ended. And that's what you saw here as well. The source of, when the source ended, when I stopped it here, it said, well, liveliness changed. I'm not sure if you're able to see it, but it says, well, there is only one alive instance earlier, and now it's back to 0. There is no one talking about a blue square. So you get this notification. So what does that mean? This is actually a stream life cycle. You know when it begins, you know when it ends, and not just one square, all the squares of that are different colors essentially. So you can manage the life cycle over a distributed system of things that are coming in and going out. The streams could be in theory infinite, but you will know when it started and when it ended. In fact, it does the same thing. We don't see it here. It also knows that it is the first instance. It's like, okay, something new thing came up. It's like there is a new flight that just came within the 10 miles of my radius. It knows that, and you can react to that. It's like, well, for any new flight, well, start drawing a little icon or something like that. So a very simple example, but it knows when things come and go. And guess what? There is another technology that helps you do exactly that. It's a database. You can create a record. You can update that record. It's like, well, change that row exactly, the customer ID, blah, change it. And at the end of it, well, this customer no longer works, or no longer, this employee no longer works, delete this record. These crude operations that we are so familiar in databases is the same applied over a stream of data. You can create, update the same object. You're talking about the same flight, the same employee, the same flight, and how it comes to life and goes on. Any question on this so far? Yeah?
Yeah. So it's maybe more about how DDS works internally. And you said that it can work over a TCP/IP, so socket communication, right? How does it deal with an unreliable link? Something continues to publish, and the link goes down, and the link is reestablished. What's happening?
Right, excellent question. So DDS in fact has excellent support for delivery, essentially data delivery. In fact, I would go to the extent it is perhaps the best middleware out there that gives you so much control on data delivery. It's in fact data distribution service. So if the link goes down, that doesn't mean the session has ended. There are various things can happen, and you are in control of that through what is called QoS, quality of service. You can change how your application wants to behave in cases like this. Okay, if one option is, well, just don't do anything. Maybe the link will come back. Maybe it's a temporary thing. So, hold your horses, and it will not announce, that this link is down and everything is dead. You cannot communicate, and it's like done. It will wait, and when a connection is established, it will keep trying. Well, I lost this guy a while ago. Is he reachable? Is he reachable? It will keep trying. I'm simplifying it quite a bit. There are protocols, essentially RTPS, that will keep that, provided you have configured it that way. And configuration is all XML. Another alternative is, well, slightly different from what you asked. I have sensor data. It's coming at just like tremendous rate, 2000 hertz, and it's just temperature or whatever. I don't need so many samples. This is not a tweet. This is not a customer by request or a transaction. I know it's pretty much going to be the same. If I lose this one, that's fine. I have another one right after. So I can configure this delivery option, this delivery mechanism to be, well, best effort. I don't need reliability of TCP all the time. I'm okay if I drop like 1 in 1000, 1 in 100 or whatever, up to your tolerance. So you can configure that. So best effort versus the reliable. You can tune that. And it goes on and on. You can say, well, between this topic and this link, save everything. I want to know what happened even after a whole world, goes down. I want to know, just persist everything. Well, okay, it will just launch a persistent service, and all the traffic that goes between those two things will be persistent. And it's just a configuration. Your program, your application did not even care and it just using configuration you can do. Does that answer your question?
More or less. If I had information that needs to be delivered in a timely manner, though, I might want to know if that link goes down. So are there still ways for me to plug in to know that the link is down?
Well, if your link is down, then, well, you cannot communicate if that's the only link you have. So you will know it is down. You can, the whole network, in a sense, the network of DDS processes will know that this thing is not reachable anymore. And it's now up to you. DDS will make sure that you know. Now it's up to you what you want to do with it,
Okay.
with this knowledge. I mean, it's not going to establish connection for you. So,
Okay.
does that answer?
I think, yeah. So what happens in the case, sorry, I mean to really, what happens in the case where the link's gone down, the publisher continues to produce more things that need to be sent over, so the link is reestablished, will it queue up basically those messages and then
Again, it's all up to
thundering
you.
herd,
It's all up to
send
you.
them all out at once?
Excellent question. So you have multiple options. First,
Okay.
exactly what you said. When the link is established, if you have some history configured, well, the publisher will say, well, this guy showed up. And this guy is asking me for history of last 600 things that went by. Well, here it is. If the new guy shows up, a late joiner, well, we are talking and then I can tell you that. There could be another subscriber, well, don't bother. I'll manage. I'll just tell me the latest thing. Well, okay, have a seat. And it will just continue that. All these things, as long as I have the history to provide, I cannot go back and tell you everything happened in this room for last 3 years. I just don't know. But I can certainly tell you what happened in last 10 minutes, and that's the thing. So it's essentially the QoS, and you can configure that. Okay, and let's look at an aggregator. So an aggregator is going to just make sure which topics it's using. Square and circle. Yeah. There's really nothing more than that. So I'm going to publish squares, I'm going to publish circles. Let's just use the same color. And I'm going to subscribe to triangles, and it's going to aggregate them. Essentially, actually use both data from both and publish values that follow both. All right. So now it's actually looking at two streams coming in. It looks like there are two different streams of triangles, but they're actually not. If you notice, the tail is a bit shorter. Earlier we had like 6 elements, 6 history depth of 6, but here is just 3 because it really gets split between the two. It's really trying to follow two shapes outside, over here. So it's kind of jumping between, as soon as an update shows up, I should go to square, I should go to circle, I should go to the square, and that's what you see here. So let's look into the code. And you have a square reader, and it's just like before, and there is a circle reader. And now I subscribe the triangle writer to both of them. Now subscribe is the idea coming from Rx. It essentially turns everything on. Essentially, the whole pipeline gets activated when you do subscribe. The examples that I use have a different name. It's just higher level functions that I'm using, not in Rx. I wrote those. And it's essentially, for composite disposable, for each subscription, there is going to be, you can delete that subscription. That's why you get a disposable. I'm just returning one disposable that when you just use dispose on that, it just goes on and deletes everything under it. So that's why this is composite disposable. it's fairly easy to just subscribe to more than one streams and just write them out to one. So that's the point. Okay, and now I have a interesting one. Now this is C#, and we have a very powerful thing called link. And well,
Use the correlator.
yeah. Alright, I'm gonna use link. So how many of you are familiar with link? Okay, excellent. So link is, so about half the number of people are in the room here. Link is a way of writing embedded queries on your data sources. It could be database, it could be a stream like this, it could be XML, it could be your data within your in-memory data structure. You can write SQL-like queries on your data sources. It's deliberately, and like any data source pretty much. Doesn't matter if it's database or something else. And you can query it. Now the most interesting part I feel is even when you have streaming data, you can still use essentially SQL pretty much, okay, to query that data. It's a bit weird concept. In a database, you have stable data, and query is run over the data, right? So query, you have data stands still and query runs. Think of it the other way around. There is data that's running, but the query is standstill. So it's the flip model. And the beauty here, because we use functional programming, I'm not going to go into details of that. You can look that up, how Rx really manages that. How a SQL-like query can be executed on a streaming data. And that's what you see. And it raises the level of abstraction so high that you can in fact just say like from square in this reader, Rx square reader, and from circle, there are two sources, right? From circle in Rx circle reader, and take one, so for every sample that comes through the square, just read one from the other one. That's what you're saying. Just read one, because I'm going to correlate those together. One to one. And when you get two of those, well, make sure they are of the same color. I don't want to correlate a blue circle with a red square and those things. I want to make sure that they are of the same color. And when that happens, just produce new value, a projection, where you use the value of x and y of the square. The color is again the square, but look at the shape size. I want the shape size to be the x of circle. So now there are two streams coming in. X is going to change for the circle, right? It's going to bounce and reduces and grows bigger and all that. You're going to see the shape is kind of shrinks and grows. So it's essentially a correlation that you can do very simply by just writing your intent. I mean, this is as simple as it can get, a SQL complete declarative specification of your program. Let's run that and make sure it happens. So I have a square, that's a blue one, and I'm going to start a circle that's also same, because without that, well, let's just start a green one, because we want to show that nothing will, well, what's that? Let me get rid of that. Suppose data, I want solid red. Okay, publish. And I'm going to subscribe to triangle, but nothing is going to happen. Not until I run this program. And what is it? Select menu. enter link. It noticed that there are things going on in the network, like there are two streams, but it's really not showing us anything because the colors are different. So now let's add a blue circle. And why isn't it moving? It's not moving very slowly. Let me get rid of this circle here. No. Let me start over. I don't know, through these multiple runs, I don't know, maybe it's in some unstable state, which it is, in fact, it's supposed to close right here. So it doesn't like any combination. Okay, here we go. Start this again. Oops. Publish blue square, blue circle. Is the other one running? Not yet. Okay. Subscribe to. There you go. Okay, that's how it's supposed to look. So now what you see is correlation. You can see that it follows the triangle, follows the square, but its shape is dependent on where the circle is. Of course, circle is, the x is higher here, and that's why as it moves here, it shrinks, and again it grows bigger, and now it shrinks. So this is, now you can, I hope you're starting to see how this can be combined, these operators can be combined. And this is like not even start to scratch the surface of Rx, what you can do. And look, I want to show like two things here. Expressiveness of this program. It's essentially a link, essentially a SQL query, very declarative. You do not write a for loop, you do not write, it's not procedural at all. But it is able to just express what it does in English, basically. I mean, not all problems are like that. It's a very purpose-made problem. But you will see that common theme in rest of the, more complicated problems where you want to express it very succinctly. There are lots and lots of other operators that you can use. You can use joins, you can use zip, transform. I think there are like 100, or maybe even more than that. So it's with all that combined together, you have a full-fledged power of a complex event processing system at your disposal. Just use C#, use a DDS for data distribution. It will let you know what's happening to your data in this whole network, and then observe it. Use Rx to observe what's happening. You get to keep the data flow end to end, and that's the point here. So I think CEP, there are several tools of course out there, very commercial successful tools that allow you to do CEP, but they are not embedded per se. You cannot just use just a piece of it and in your program and just be done with it. But this really offers you that possibility, a very real possibility. This particular demo and other things are actually online and on GitHub. I'm going to have these slides on SlideShare, also in the Silicon Valley, speaker notes kind of section there. So you can find out. There's a lot more I can talk about. I couldn't cover most of the details. It's like, what is this functional thing, and then what is DDS. I just brushed through several topics, but I hope this is pretty much all I have got. If you have any other questions, feel free to ask. And well, thanks for coming. Thanks for watching the demo.